66 million years ago, on an ordinary spring morning in what would one day be called the Cretaceous period, a rock the size of a mountain was hurtling toward Earth at 20 kilometers per second. It had traveled for millions of years through the cold silence of space, its trajectory shaped by an almost infinite chain of gravitational interactions. The pull of Jupiter, the nudge of passing comets, the slow wobble of its own spin. None of that history mattered anymore. What mattered was that in approximately 4 hours, this 10-kilometer sphere of carbonite and iron would strike the shallow seas off what we now call the Yucatan Peninsula, and it would change everything. The impact released the energy of 100 million nuclear weapons. It vaporized billions of tons of rock, sulfur, and seawater. It launched a cloud of debris into the stratosphere that would circle the globe within hours. Wildfires swept across continents. Tsunamis hundreds of meters high crashed against coastlines thousands of kilometers from the impact site. And then came the darkness, a years-long twilight as the sun vanished behind a shroud of dust and sulfur aerosols. Global temperatures dropped by nearly 30 degrees Celsius. The plants died first, unable to photosynthesize. Then the herbivores that depended on them. Then the predators that depended on the herbivores. Within a geological instant, 3/4 of all species on Earth were gone, including every dinosaur larger than a house cat. That is what happened. That is the history written in stone, in the thin layer of iridium-rich clay that marks the boundary between the Mesozoic and Cenozoic eras, in the 200-kilometer scar buried beneath the sediments of the Yucatan. But tonight, we are going to imagine a different history. We are going to ask what would have happened if that rock, that mountain falling from the sky, had missed. And it nearly did. Or rather, it nearly could have. The specific trajectory of any asteroid depends on countless variables stretching back billions of years. A change in any one of them would have produced a different outcome. Some researchers have calculated that if the Chicxulub impactor had arrived just minutes earlier or later, it would have struck deep ocean rather than shallow coastal waters. Less vaporized rock, less sulfur in the stratosphere, a regional catastrophe rather than a global extinction. The dinosaurs would have woken up the next morning to a world shaken but not destroyed, and they would have continued doing what they had been doing for the previous 165 million years, dominating every terrestrial ecosystem on the planet. So before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And let me know in the comments where you are tuning in from. I am always curious to see how far these stories travel. Now dim the lights if you have not already. Take a deep breath and let the modern world fade away. Listen for the sound of wind through Cretaceous ferns. The rustle of a world preparing to continue rather than end. This is the story of 66 million years that never happened, and we are going to walk through every step of it together. The discovery that an asteroid killed the dinosaurs is itself a remarkable story, and it is worth telling briefly because it shows how science works, how a radical idea dismissed at first as fantasy can become accepted fact when the evidence accumulates. In 1980, a physicist named Luis Alvarez and his geologist son Walter were studying rock formations near Gubbio, Italy. They were examining the thin layer of clay that marks the Cretaceous-Paleogene boundary. They found something strange. Iridium, and lots of it, 30 times the normal concentration. Iridium is rare on Earth's surface because most of it sank into the planet's core billions of years ago when the Earth was still molten. But it is common in asteroids. The Alvarez team proposed that a massive impact had occurred at exactly the moment the dinosaurs disappeared, and they predicted that somewhere on Earth there should be a crater to prove it. The scientific community was skeptical at first. Many geologists preferred volcanic explanations. The Deccan Traps in India had been erupting for millions of years around the same time, pouring enough lava to cover half of modern India in basalt kilometers thick. Surely that was enough to explain a mass extinction. But the Alvarez team kept gathering evidence, and other researchers joined the hunt for the crater. In 1978, a geophysicist named Glenn Penfield had noticed something odd while surveying for oil in the Yucatan. A vast circular structure buried beneath the sediments, visible only in gravity and magnetic anomaly maps. He did not know what it was, but he suspected it might be an impact crater. It took another decade for the connection to be made, for samples from Mexican oil wells to be tested and found to contain shocked quartz and tektites, minerals that form only under the extreme pressures of an asteroid impact. By 1990, the case was closed. The crater was real. It was exactly the right age. And it was exactly the right size to have caused the extinction. But here is the thing about asteroid impacts. The thing that makes our thought experiment possible. They are not inevitable. They are not destiny. They are contingency, pure and simple. The result of orbital mechanics and gravitational perturbations playing out over time scales so vast that the outcome might as well be random. The Chicxulub impactor could have arrived a few minutes earlier and splashed into deep water. It could have arrived a few hours later and struck the middle of the Pacific. It could have missed Earth entirely, sailing past our planet and continuing on into the outer solar system, never to return. In any of those scenarios, the dinosaurs would have survived. Not because they were destined to survive, but because the particular event that killed them simply would not have occurred. Our story begins in that alternative moment. The asteroid screams through Earth's atmosphere, carving a white-hot trail across the sky, visible from 1,000 kilometers away. It strikes the Pacific Ocean, 2,000 kilometers from the nearest coastline. The impact generates tsunamis that devastate coastal regions across the Americas and Asia. Millions of creatures die. Ecosystems are disrupted for decades, but the sulfur stays in the ocean. The dust settles within months rather than years. The sun keeps shining, the plants keep growing, and the dinosaurs, the tyrannosaurs and triceratops, the hadrosaurs and ankylosaurs, the tiny feathered maniraptorans darting through the underbrush. They continue their ancient reign as if nothing had happened. Because for them, nothing significant has happened. They have survived worse. They have survived the volcanic winters of the Deccan eruptions, the gradual cooling of the late Cretaceous, the shifting continents and changing sea levels that have been reshaping their world for millions of years. They are the most successful group of large land animals the planet has ever produced, and they show no signs of decline. Their diversity is at its peak. Their body sizes range from chicken-sized insectivores to 40-ton herbivores. They occupy every ecological niche from Arctic forests to tropical swamps. They have been doing this for 165 million years, and there is no biological reason why they cannot continue for 165 million more. The world belongs to the dinosaurs, and now, for the first time in Earth's history, we are going to see what they would have done with it. To understand what might have been, we first need to understand what was. We need to step back from the alternative history we are constructing and look clearly with remarkable precision. The ruler of this world was Tyrannosaurus rex. And it is worth spending a moment really seeing this animal as it was, not as the lumbering tail dragger of old reconstructions, but as something far more terrifying and far more beautiful. 12 meters long from snout to tail, 9,000 kilograms of muscle and bone, supported on legs built like a sprinter's, designed for explosive acceleration rather than sustained running, a skull large enough to swallow a human being whole, lined with teeth the size of bananas, each one serrated like a steak knife, each one capable of punching through bone as easily as you might bite through an apple. But the most remarkable feature was the eyes. Tyrannosaurus rex had forward-facing eyes set in a skull that was narrow at the front, giving it binocular vision, depth perception. Something rare among dinosaurs. A study by vision researcher Kent Stevens calculated that its visual acuity exceeded that of modern hawks, that it could spot prey from 6 kilometers away, that its ability to judge distance was among the best of any animal that has ever lived. This was not a scavenger waiting for something to die. This was an apex predator with the sensory equipment of a precision hunter. But Tyrannosaurus rex was the exception among predators, not the rule. The Hell Creek ecosystem supported a whole range of carnivores filling different niches. Smaller tyrannosaurs that may have hunted in groups, dromaeosaurids with their famous sickle claws, and troodontids. Those strange, large-eyed hunters whose brains relative to their body size were larger than any other dinosaur group. We will come back to the troodontids later, because they matter enormously to our story. For now, just note that they existed, small, smart, watching the world with eyes that saw more than most. The herbivores were even more diverse. And among them, small ornithopods browsing in the undergrowth, oviraptorosaurs tending their nests, tiny mammals scurrying through the leaf litter at night. Above this world flew the pterosaurs, and we need to pause here because the pterosaurs are not dinosaurs. They are a separate lineage entirely, related but distinct. Like cousins rather than siblings. The largest of them was Quetzalcoatlus, named after the Aztec feathered serpent god. And when I tell you that its wingspan reached 11 meters, I need you to actually picture that. Wider than a small airplane. larger than any flying animal that has ever existed before or since. Standing on all fours, it would have looked a giraffe in the eye, yet its bones were hollow, honeycombed with air pockets, so lightweight that this creature the size of a small aircraft probably weighed only about 250 kilograms, less than many adult humans. It probably hunted like a giant stork, stalking across floodplains on folded wings, snatching up small dinosaurs and mammals and fish with a beak the length of a human arm. And what about the mammals? They were there. They had been there all along, evolving alongside the dinosaurs from the very beginning, sharing the planet for over 150 million years. But they were small. The largest known Cretaceous mammal was perhaps the size of a badger. Most were the size of mice or rats, creeping through the underbrush, climbing trees at night, hunting insects and seeds in the ecological shadows cast by the giants. They were not failures. They were highly successful at what they did, but what they did was stay out of the way. The niches they occupied were the niches the dinosaurs did not want. The nocturnal niche, the burrowing niche, the tiny insectivore niche. Everything else belonged to the ruling reptiles. This was the world on the morning the asteroid missed. A world of warmth and abundance, of continental drift and shallow seas, of theropod hunters and ceratopsian herds and pterosaurs soaring on thermals above it all. A world that had been refining itself for over 165 million years. That showed no signs of decline. That was, if anything, at the peak of its diversity and success. The dinosaurs were not waiting to be replaced. They were not evolutionary dead ends stumbling toward inevitable extinction. They were the most successful group of large land animals the planet had ever produced, and they had every reason to expect that their reign would continue indefinitely. It almost did not, of course. In our timeline, the rock from space ended everything. But in the timeline we are exploring tonight, the rock splashed harmlessly into the Pacific, and the dinosaurs woke up the next morning to continue what they had been doing for 165 million years. The question now is, what would they have done with another 66 million years of evolution? What would they have become? To answer that, we need to understand something that the dinosaurs themselves could not have known. The world was about to change, not suddenly, not catastrophically, but slowly and inexorably over tens of millions of years. The warm, stable climate of the Mesozoic was ending. A long cooling was coming, driven by the slow drift of continents, by the rise of mountains, by the circulation of ocean currents that would eventually lock Antarctica in ice. New plants were evolving, grasses, which would spread across the world and transform every ecosystem they touched. The dinosaurs were about to face challenges they had never encountered in 165 million years of evolution. Challenges that would test their adaptability in ways the asteroid never could. But first, let us look at why the dinosaurs were so dominant in the first place, and why the mammals could not seem to break out of their ecological shadows. The answer is not what you might think. There is a story that gets told in countless documentaries and textbooks, a comfortable narrative that explains why the world looks the way it does today. It goes something like this. The dinosaurs were lumbering, cold-blooded failures, evolutionary dead ends that dominated only because nothing better had come along yet. They were big and dumb, slaves to their instincts, unable to adapt to changing conditions. When the asteroid struck, it simply cleared the stage for the true inheritors of the Earth. The mammals, warm-blooded and intelligent, who had been waiting patiently in the wings for their moment to shine. The extinction was almost a mercy, a necessary reset that allowed evolution to finally get things right. This story is almost entirely wrong. And understanding why it is wrong is essential to understanding what would have happened if the dinosaurs had survived. The dinosaurs were not failures waiting to be replaced. They were an evolutionary triumph of staggering proportions. arguably the most successful group of large land animals the planet has ever produced. They dominated terrestrial ecosystems for over 165 million years. Try to wrap your mind around that number for a moment. Anatomically, modern humans have existed for perhaps 300,000 years. The entire genus Homo, including all our extinct relatives, goes back maybe 2.5 million years. The dinosaurs reigned for 66 times longer than that. They evolved into thousands of species, filled every conceivable ecological niche from tiny insectivores to 40-ton browsers, spread across every continent, adapted to every climate from tropical rainforests to polar winters, and they showed absolutely no signs of decline in the millions of years before the asteroid struck. If anything, their diversity was increasing. The late Cretaceous was not a period of dinosaurian senescence. It was a golden age. So why did mammals stay small? Why, after 150 million years of coexistence with dinosaurs, had they not produced anything larger than a badger? The traditional answer is simple. The dinosaurs were suppressing them. The big niches were occupied by big dinosaurs, and the mammals simply could not compete. They were forced into the margins, into the night, into burrows and treetops where the giants could not follow. Remove the dinosaurs and the mammals would explode into all that newly vacant ecological space. This explanation has a certain intuitive appeal, but recent research suggests it is incomplete at best, and possibly backward. A 2021 study from Oxford and Birmingham universities analyzed the evolutionary constraints on different mammal groups before and after the extinction, using sophisticated statistical methods to identify where each lineage was hitting ecological limits. What they found was surprising. The ancestors of modern placentals and marsupials, the groups that would eventually produce everything from whales to elephants to humans, were not primarily competing with dinosaurs. They were being outcompeted by other mammals. The Mesozoic was not just home to the tiny shrew-like creatures we usually imagine when we think of early mammals. It hosted a remarkable diversity of mammalian lineages, most of which are now completely extinct. Multituberculates, gondwanathurians, eutriconodonts, dryalstids. These animals had already claimed many of the small to medium body size niches. Some were gliders, some were swimmers, some were burrowers. Some had teeth specialized for cracking hard foods, others for slicing meat, others for grinding plants. The ancestors of modern mammals were not being held back by distant dinosaurian over Mount Everest while mammals gasp for air at base camp. This is why sauropods could grow to 50 tons, while the largest land mammals have never exceeded 20. The dinosaurs were not just occupying the large body niches. They were physiologically superior at being large. They also had hollow bones, pneumatized with air pockets connected to their respiratory system, making their skeletons lighter relative to their strength than any mammal could achieve. They had faster growth rates, reaching adult size in years rather than the decades required by similarly sized mammals. They laid eggs, which meant they did not have to carry their developing young inside their bodies. A pregnant sauropod would have been a biomechanical impossibility, but an egg-laying one could produce dozens of offspring per year. Every aspect of their biology was optimized for the ecological roles they had been filling for 165 million years. A mammal trying to evolve into a large herbivore in this world would have faced competitors who could breathe more efficiently, grow faster, reproduce more quickly, and carry less weight per unit of structural strength. It is not that mammals were inferior as a group. They were simply trying to compete in a game where the rules favored a different body plan. Put mammals in the ecological vacuum left by the extinction. Give them 66 million years without competition, and they will produce elephants and whales and giant ground sloths. Keep the dinosaurs around, and the mammals will remain what they had always been: small, nocturnal, ecologically marginal. This is the world our alternative timeline inherits, not a world where dinosaurs are fragile relics clinging to existence, but a world where they are the undisputed masters of every terrestrial ecosystem, where their biological advantages make them essentially unassailable in the niches they occupy, where mammals are locked into their traditional roles by competitive pressure from multiple directions. The dinosaurs did not win their throne by accident or by default. They won it by being extraordinarily good at what they did, and nothing about the asteroid's near miss would have changed that. But here is where the story gets interesting. The dinosaurs' dominance was built on a foundation of stable, warm climate that had persisted throughout the Mesozoic era. For 165 million years, the Earth had been a greenhouse world, warm from pole to pole, humid, forested, with relatively little seasonal variation. The dinosaurs had evolved in this world and were exquisitely adapted to it. They had never faced an ice age. They had never seen a grassland. They had never experienced the kind of dramatic climate swings that would characterize the coming Cenozoic. The world was about to change in ways the dinosaurs had never encountered. The continents were drifting into new configurations, opening ocean gateways that would alter circulation patterns around the globe. Antarctica was separating from South America, and within a few million years, a cold current would begin circling the southern pole, isolating an entire continent and seeding it with ice. The Himalayas were about to rise as India crashed into Asia, their weathering rocks drawing carbon dioxide from the atmosphere and cooling the planet. Grasslands were about to spread across continents, creating entirely new ecosystems with entirely new selective pressures. The dinosaurs had proven themselves masters of the Mesozoic world. The question that our alternative history must answer is whether they could have mastered the Cenozoic world too. A world colder, drier, more seasonal, more variable than anything they had experienced in their long evolutionary history. A world that would have tested their adaptability in ways the asteroid never did. That would have demanded innovations their lineage had never before been required to produce. They had 66 million years to find out. Let us see what they might have done with them. 10 million years have passed since the asteroid missed, and if you could somehow travel back to this world, you might not notice anything different at first. The continents have not moved much. Continental drift operates on time scales of centimeters per year, And 10 million years is not enough to rearrange geography in any dramatic way. The climate is still warm, still humid, still tropical even at high latitudes. The forests still stretch from pole to pole, dense and green and dripping with moisture. It looks at first glance like the Cretaceous world we left behind, but evolution does not stand still. Even when the world seems unchanged, 10 million years is an enormous span of time, longer than the entire existence of the genus Homo, longer than the time separating the first stone tools from the smartphone in your pocket. Species do not remain static over such periods. They drift, they adapt, they specialize, they diverge. The dinosaurs of 10 million years post-asteroid would not be identical to the dinosaurs of the Cretaceous, even if their world remained superficially the same. The most significant change in this period would not have been the dinosaurs themselves, but the plants they depended on. The flowering plants, angiosperms, had been spreading throughout the Cretaceous, diversifying and competing with the older conifers and ferns that had dominated Mesozoic forests. Without the catastrophic disruption of the extinction event, this process would have continued unabated. The angiosperms had advantages that made their eventual dominance almost inevitable. They could reproduce faster, evolve more quickly, form more intimate relationships with pollinators and seed dispersers. By 10 million years after our divergence point, they would have conquered most of the world's forests, and many of them would have been bearing fruit. Fruit is one of evolution's great innovations, a bribe offered by plants to animals. Eat this sweet, nutritious flesh, and carry my seeds somewhere else in your gut. Deposit them with a pile of fertilizer. Give them a head start in life. It is a strategy that works spectacularly well, which is why it evolved independently in so many plant lineages. In our timeline, the explosion of fruit-bearing plants in the early Cenozoic helped drive the evolution of fruit-eating mammals, the primates who would eventually give rise to us. In our alternative timeline, the same opportunity would have been available, but the animals best positioned to exploit it would not have been mammals. They would have been dinosaurs. The pods were better positioned to do so than any mammal of the period. But not all the changes would have been in the canopy. Down on the forest floor, the great herbivorous dynasties of the Cretaceous would have been continuing their own evolution. responding to the changing composition of the plant communities they depended on. The hadrosaurs, the duck-billed dinosaurs, had evolved the most sophisticated plant processing equipment of any dinosaur lineage. Dental batteries containing hundreds of interlocking teeth, constantly being replaced, capable of grinding tough vegetation with an efficiency that no other dinosaur could match. As the flowering plants spread with their different textures and nutritional profiles, the hadrosaurs would have adapted right alongside them. Some lineages might have become more specialized, focusing on particular types of plants in particular habitats. Others might have become more generalized, capable of thriving on whatever vegetation was available. The key point is that they would not have stood still. Evolution never does. The ceratopsians, too, would have continued their radiation. In the late Cretaceous, they had already diversified into dozens of species across North America and Asia, varying in size from dog-sized to elephant-sized, sporting an astonishing variety of horn and frill configurations. Without the extinction, this diversity would have continued to expand. Perhaps some lineages would have become larger, filling niches that in our timeline would eventually be occupied by elephants and rhinoceroses. Perhaps others would have become smaller, more nimble, adapted to different habitats or different food sources. And the sauropods, those long-necked giants that had defined the Jurassic but seemed to be declining in diversity by the late Cretaceous, would have persisted as well. They were specialists, reaching food sources that no other herbivore could access, and as long as tall forests existed, they would have had a role to play. In our timeline, the extinction removed them before we could see how they might have adapted to a changing world. In our alternative timeline, they would have had the chance to prove their staying power. The world of 10 million years post-asteroid would have been recognizable to a visitor from the Cretaceous, but it would have been subtly different in 1,000 small ways. New species where old ones had been, new behaviors, new ecological relationships, new forms filling new niches. The dinosaurs were not changing because the world forced them to change. The world was still warm, still forested, still fundamentally Mesozoic in character. They were changing because that is what life does. It explores possibilities. It fills available space. It diversifies. But the real changes were coming. Around 55 million years ago, the planet was about to experience something unprecedented. A sudden dramatic warming that would push global temperatures to levels not seen in tens of millions of years. The Paleocene-Eocene thermal maximum was approaching, and it would test the dinosaurs in ways they had never been tested before. Around 55 million years ago, something extraordinary happened to the Earth's climate. Within perhaps 20,000 years, a blink of an eye in geological time, global temperatures spiked by 5 to 8 degrees Celsius. The polar regions, already warm by modern standards, became positively tropical. Palm trees grew in Alaska. Crocodilians basked on the shores of the Arctic Ocean. The deep oceans warmed by several degrees, fundamentally altering circulation patterns and marine ecosystems around the world. Scientists call this event the Paleocene-Eocene thermal maximum, and it was one of the most dramatic climate shifts in the last 100 million years of Earth history. The cause was almost certainly a massive release of carbon into the atmosphere, perhaps from volcanic activity associated with the opening of the North Atlantic, perhaps from the destabilization of methane hydrates on the ocean floor, perhaps from some combination of both. The result was a greenhouse effect more intense than anything the dinosaurs had experienced since the Triassic. It was a test, and in our timeline, it reshaped mammalian evolution dramatically. Many species went extinct. Others shrank in size because smaller bodies are easier to cool. New lineages appeared, adapted to the hothouse conditions. The primates that would eventually give rise to monkeys and apes first appear in the fossil record right around this time, as if the thermal crisis had opened new ecological doors even as it closed others. In our alternative timeline, the same crisis would have occurred. The thermal maximum was driven by geological processes that had nothing to do with the asteroid impact, but it would have been dinosaurs, not mammals, facing the challenge. And here is the interesting thing. Dinosaurs might have been better equipped to handle extreme heat than mammals were. Think about the problem from a physiological perspective. Mammals are endotherms. They generate their own body heat internally and work hard to maintain a constant internal temperature, usually around 37 degrees Celsius. This is metabolically expensive and requires sophisticated cooling mechanisms. Sweating, panting, seeking shade, restricting activity to cooler parts of the day. When ambient temperatures approach or exceed body temperature, these mechanisms become less effective. A mammal in extreme heat is working against thermodynamics, trying to dump heat into an environment that does not want to accept it. Large dinosaurs operated differently. They were probably gigantotherms. Their sheer mass meant that their body temperature remained relatively stable regardless of external conditions, like a massive water tank that takes hours to warm up or cool down. They did not need to generate as much metabolic heat as mammals, because they could absorb heat from their environment during the day and retain it through the night. And because they did not maintain the high constant temperatures that mammals require, they were not as vulnerable to overheating when the world got hot. The smaller dinosaurs had their own advantages. Many of them were feathered, and feathers are remarkably versatile insulators. They can be fluffed up to trap warm air in cold conditions, or sleeked down and spread to allow heat dissipation in hot conditions. The same structure that would later help dinosaurs survive polar winters might have helped them survive equatorial summers during the thermal maximum. The tropical regions during the Eocene hothouse might have become challenging even for dinosaurs, perhaps forcing migrations toward the poles, perhaps creating equatorial dead zones where temperatures simply exceeded what any large land animal could tolerate. But the poles themselves would have become paradise, warm, wet, covered in lush forests extending nearly to the Arctic and Antarctic circles, perfect habitat for dinosaurs of all sizes, expanding into regions that had previously been marginal. But the land was not the only arena where evolution was playing out. In the oceans, our alternative timeline would have featured something that our actual history lacks entirely: the continued evolution of the great Mesozoic marine reptiles. In our timeline, the mosasaurs and plesiosaurs went extinct at the boundary, victims of the same catastrophe that killed the land dinosaurs. The niches they left empty would eventually be filled by whales, which evolved from land-dwelling mammals over the course of the Eocene, one of evolution's great transformations. But in our alternative timeline, the marine reptiles never went extinct. They would have been there already, occupying those niches, when the thermal maximum reshaped the oceans. The mosasaurs where land met sea, another group would have been thriving: the pterosaurs. In our timeline, they went extinct alongside the dinosaurs, leaving the skies to the birds, but in our alternative history, they would have persisted, and the warm, productive seas of the Eocene would have been ideal habitat for them. Picture a pterosaur the size of a small airplane soaring over tropical waters, plucking fish from the surface with a beak the length of a human arm. Picture colonies of smaller pterosaurs nesting on sea cliffs, filling the ecological roles that seabirds occupy in our world. Picture the skies of the Eocene shared between the pterosaurs and the birds, both dinosaur lineages technically, but so different in form and history that they would have competed for some niches while dividing others. The Eocene hothouse lasted for millions of years, long enough for evolution to produce countless adaptations to its conditions. Somewhere around 50 million years ago in our alternative timeline, the dinosaurs would have reached a kind of equilibrium with this warm world, diversified across every continent, dominant in nearly every terrestrial and aerial niche, sharing the oceans with their marine reptile cousins. It might have seemed to an observer at that moment that this was simply how the world worked, that dinosaurs were as permanent a feature of the Earth as the mountains and seas. But the climate does not stay constant forever. Even as the dinosaurs were flourishing in their hothouse Eden, the processes that would end it were already underway. India was crashing into Asia, raising the Himalayas, and the weathering of those new mountains would begin drawing carbon dioxide from the atmosphere. Antarctica was drifting toward the South Pole, and soon a new ocean current would isolate it from the warmth of the tropics. The long cooling was about to begin, and it would transform the Earth more profoundly than any asteroid ever could. The Oligocene cooling was a test unlike any they had experienced before. But here is where we need to challenge a common assumption. We tend to think of dinosaurs as tropical animals, creatures of warm climates that could not possibly survive in cold conditions. After all, they are often depicted in steaming jungles, their massive bodies soaking up the warmth of a prehistoric sun, and the comparison to modern reptiles seems to reinforce this impression. Snakes and lizards do not do well in cold climates, which is why you do not find them in Antarctica. The problem with this assumption is that it is almost certainly wrong. We now know that dinosaurs lived in polar regions during the Mesozoic. Fossil sites in Alaska and Antarctica have yielded dinosaur bones from latitudes that would have experienced months of winter darkness, temperatures that regularly dropped below freezing. These were not occasional visitors or lost wanderers. They were established populations, breeding and raising their young in conditions that we would consider harsh by any standard. The famous Prince Creek Formation in northern Alaska preserves a diverse dinosaur ecosystem from about 70 million years ago, including hadrosaurs, ceratopsians, and tyrannosaurs, all living year-round above the Arctic Circle. How did they do it? The answer was literally covering their bodies, feathers. We have known for decades now that many dinosaurs were feathered, not just the small bird-like theropods, but a surprisingly diverse range of species. Feathers have been found on tyrannosaurs, on ornithischians, on dinosaurs large and small from lineages across the family tree. The original function of feathers was not flight, it was insulation. They evolved to keep dinosaurs warm, to trap body heat against the skin, to allow these animals to remain active in conditions that would have sent a naked reptile into torpor. In our alternative timeline, this adaptation would have proved crucial as the world cooled. The feathered theropods, already equipped with nature's most versatile insulation, would have been able to expand into colder habitats as the ice advanced. Picture a pack of medium-sized theropods, their bodies covered in thick plumage that ruffles in the frigid wind, hunting across a snowy landscape that would have been unthinkable in the Mesozoic. These creatures would have looked remarkably bird-like, because they were essentially birds that had never given up hunting on the ground. The larger dinosaurs faced a different challenge. A 15-meter sauropod could not rely on feathers for insulation the way a 2-meter theropod could. The surface area to volume ratio does not work in their favor, but gigantothermy cuts both ways. The same thermal inertia that helped large dinosaurs survive the Eocene heat would have helped them survive moderate cold. Their massive bodies would have changed temperature so slowly that short cold snaps would not affect them much. They might have migrated seasonally, following the warmth and the food, the way many large mammals do today, or they might have simply become restricted to equatorial regions, ceding the higher latitudes to their smaller, more adaptable relatives, the ornithischians. The ceratopsians, hadrosaurs, and ankylosaurs present an interesting question. We do not have direct evidence that they were feathered, though some specimens suggest they had filamentous integuments that might have served a similar purpose. In our alternative timeline, the selective pressure of cooling climates might have driven the evolution of thicker, more insulating body coverings in these lineages. Picture a ceratopsian of the Oligocene, its body covered in a dense coat of proto-feathers, its massive frill perhaps reduced from the elaborate displays of its Cretaceous ancestors to something more practical, more streamlined against the cold. It would have looked something like a woolly rhinoceros, but with the unmistakable silhouette of a horned dinosaur. But the most profound change was not in the dinosaurs themselves. It was in the world they inhabited. As the climate cooled and dried, the endless forests began to break up. Trees require certain minimum temperatures and rainfall amounts to thrive. And as these conditions retreated toward the equator, the forests retreated with them. In their place, something new was appearing. Open landscapes, woodlands with gaps between the trees, meadows and clearings where sunlight reached the ground. These were not yet the great grasslands that would later transform the planet, but they were the beginning of something. The age of forests was drawing to a close, and the age of open spaces was beginning to dawn. For dinosaurs that had spent 150 million years in forests, this was a profound environmental shift. The rules of survival were changing. In a forest, you can hide. You can ambush prey or avoid predators by staying out of sight. Size matters less than stealth, and speed matters less than maneuverability. But in an open landscape, there is nowhere to hide. You survive by being fast enough to escape, or big enough to fight, or vigilant enough to spot danger before it is too late. Herding becomes an advantage, because many eyes are better than two. Long-distance running becomes more valuable than short sprints. These are exactly the pressures that would reshape mammal evolution in our timeline, producing the horses and antelope, the wolves and big cats that came to dominate open ecosystems. In our alternative timeline, the same pressures would have acted on dinosaurs. The results might have been startlingly similar, not because dinosaurs would have evolved into mammals, but because the same ecological problems tend to produce similar solutions. A fast-running herbivore is a fast-running herbivore, whether it is a horse or an ornithomimid. A pack-hunting predator is a pack-hunting predator, whether it is a wolf or a derived theropod. The Oligocene was a transition, a bridge between the warm forests of the Eocene and the grasslands that were coming. The dinosaurs that emerged from it would have been different from their Cretaceous ancestors, better adapted to cold, better adapted to open spaces, beginning to develop the specializations that the new world would demand. They had survived their first major test, but the real transformation was still to come. Around 23 million years ago, a humble family of plants would begin a conquest that would reshape every continent except Antarctica. Grass was about to change everything. Grass does not seem like a revolutionary organism. It is humble, low to the ground, easily overlooked. You walk on it, mow it, forget it exists. But starting around 23 million years ago in the early Miocene, grass began a conquest that would transform the face of the Earth more thoroughly than any asteroid impact. By the time it was done, grass would cover roughly 40% of the planet's land surface and create entirely new ecosystems that had never existed in the first 400 million years of life on land. To understand why grass was so revolutionary, you need to understand what makes it different from other plants. Most plants grow from their tips. Damage the top of a tree and you have removed its growing point, stunted its development, perhaps killed it entirely. But grass grows from its base. You can cut it, burn it, graze it down to stubble, and it simply regrows from below. This makes grass almost impossible to kill through browsing or fire. It is the plant equivalent of a hydra. Remove its head and it grows right back. Grass also produces silica phytoliths, microscopic particles of glass embedded in its of evolution in grassland ecosystems. In our alternative timeline, the grasslands would have spread just as they did in our history. The climate patterns that created them had nothing to do with what animals were present. The difference is that it would have been dinosaurs, not mammals, facing the challenge of adapting to this new world. And the pressures would have been identical: eat grass or starve, run fast or die, see predators coming or become prey. The solutions, driven by the implacable logic of natural selection, would likely have been remarkably similar. Consider the ceratopsians, the horned dinosaurs that had dominated the herbivore niches of late Cretaceous North America. In the forests, they had been browsers, using their parrot-like beaks to crop vegetation and their shearing teeth to process it. But those teeth were not designed for grass. They would have worn down quickly against the silica-laden tissues, leaving the animals unable to feed efficiently. The ceratopsians that survived in a grass-dominated world would have been those that evolved solutions to this problem. One possibility: the evolution of ever-growing teeth, similar to those of rodents and horses. The developmental pathways for continuous tooth growth exist in dinosaurs. We see hints of it in the dental batteries of hadrosaurs, where teeth were constantly being replaced from below. A ceratopsian lineage that evolved truly hypsodont teeth would have been able to graze indefinitely, wearing down its teeth against the grass and simply growing more to replace them. Picture a descendant of Triceratops. 20 million years evolved from its Cretaceous ancestor. It is still recognizable as a ceratopsian. The basic body plan works too well to abandon, but the proportions have changed. The head is longer, lower to the ground, adapted for grazing rather than browsing. The beak is wider, more squared off, designed to crop grass in broad swaths like a living lawn mower. The frill has shrunk, no longer needed for display or thermoregulation in the same way. The energy instead invested in the massive jaw muscles needed to process tough vegetation. It moves in herds of hundreds across the Miocene prairies. A river of flesh and horn flowing across the landscape, like wildebeest across the Serengeti. But grazing brings its own dangers. In a forest, you can hide from predators. On an open plain, you are visible from kilometers away. The only defenses are vigilance, numbers, and speed. The herding behavior of Miocene ceratopsians would not have been optional. It would have been essential for survival. A lone grazer on an open plain is a dead grazer. A herd of 1,000 with hundreds of eyes scanning the horizon has a chance. The ornithomimosaurs, the ostrich dinosaurs of the Cretaceous, were already pre-adapted for grassland life in some ways. They were fast runners with long legs and light builds. They were probably omnivorous, able to exploit a variety of food sources. In a world of open plains, they might have become the ecological equivalents of antelope and gazelles. Fast, alert, living in herds, relying on speed to escape predators. Imagine a Miocene ornithomimid, its legs even longer than its ancestors. Its body streamlined for sustained running across flat terrain, its neck long enough to see over the grass, to spot danger approaching from any direction. It feeds on a mixture of grass seeds, insects, and small animals, an opportunistic diet that allows it to thrive in environments too harsh for specialists. When threatened, it can reach speeds of 60 kilometers per hour, fast enough to outrun any predator that relies on pure pursuit. It lives in groups of dozens. And when one individual spots danger and bolts, the others follow instantly. A wave of panic spreading through the herd faster than any predator can react. The hadrosaurs present an interesting case. Their sophisticated dental batteries, those rows of hundreds of interlocking teeth, were already the most efficient plant processing machinery any dinosaur had ever evolved. In some ways, they were pre-adapted for grazing, capable of handling tough vegetation that would have defeated other herbivores. Perhaps in our alternative timeline, the hadrosaurs would have become the dominant grazers, their existing adaptations giving them a head start in the competition for grass. But there is another possibility, one that seems more likely given the rules of evolutionary competition. Perhaps no single lineage would have dominated. Perhaps the Miocene grasslands would have been partitioned among multiple dinosaur groups, each specializing in slightly different niches, just as the African savanna today is shared among wildebeest, zebra, buffalo, gazelle, and a dozen other species, each exploiting the grassland in its own way. The ecological theater had been rebuilt. The forest stage that had hosted the Mesozoic drama was being struck, replaced by an endless plain of waving grass under an open sky. New roles were available for any actors willing to learn new lines. The dinosaurs had spent 150 million years mastering forest life. Now they had perhaps 20 million years to master something entirely different. The question was, what would be hunting them? Because in a world of fast-running herds, the predators would have to change too. Tyrannosaurus rex was the apex predator of the late Cretaceous. 12 meters of muscle and bone, 6 tons of killing power, a bite force that could crush a car. It was built for one thing, taking down large prey through overwhelming force. In the forests of the Mesozoic, where ambush was possible and prey could not see you coming until it was too late, this strategy worked magnificently. Tyrannosaurus rex sat at the top of its food chain for millions of years, unchallenged, seemingly perfect. But perfection is always relative to environment. Change the environment and perfection becomes obsolescence. The open grasslands of the Miocene would have been hostile territory for a classic tyrannosaur. In a forest, a 6-ton predator can hide behind trees, can approach within striking distance before its prey even knows it is there. On an open plain, there is no hiding a predator that stands 4 meters tall at the hip. Prey animals can see you coming from kilometers away. By the time you get close enough to attack, they are already running. And you, with your massive body and relatively that contain many predators alongside their apparent prey, but it is ambiguous. Some paleontologists think tyrannosaurs were social hunters. Others think they were solitary. perhaps only coming together to scavenge or breed. In the absence of certainty, we have to reason from ecological principles. And ecological principles suggest that grassland tyrannosaurs would almost certainly have become pack hunters. Not because there is anything magical about grasslands, but because the prey they would have been hunting, large, dangerous, herd-dwelling dinosaurs, would have been almost impossible to take any other way. The selective pressure would have been intense. Individuals that could cooperate would have eaten. Individuals that could not would have starved. Over millions of years, that is enough pressure to reshape behavior, to build brains capable of coordination and communication, to create social structures that had not existed before. Picture a pack of Miocene tyrannosaurs, perhaps 6 or 8 individuals, moving across the grassland in the early morning light. They are smaller than their Cretaceous ancestors, maybe 7 meters long instead of 12, 3 tons instead of 6, but they are faster, more agile, working together with a coordination that Tyrannosaurus rex never needed. They have spotted a herd of grazing ceratopsians in the distance, and now they are spreading out, some circling wide to cut off escape routes, while others approach more directly to drive the herd toward the ambush. When they attack, it is not the overwhelming assault of a single giant predator, but a coordinated strike from multiple angles, each individual knowing its role, working together to bring down prey that none of them could kill alone. But the tyrannosaurs were not the only theropod lineage adapting to the grasslands. The smaller predators, the dromaeosaurids, the troodontids, the other maniraptoran theropods, would have been evolving alongside them, filling different niches in the new ecosystem. In some ways, these smaller predators were better pre-adapted to grassland hunting than the tyrannosaurs were. They were already fast runners. Many of them already seem to have been social, hunting in groups based on the fossil evidence we have. They had grasping hands that could manipulate objects, forward-facing eyes that provided excellent depth perception, and relatively large brains for their body size. The grasslands would have rewarded all of these traits. The dromaeosaurids, the raptor dinosaurs popularized by Jurassic Park, would have been particularly well-suited to pack hunting on the open plains. They were already pursuit predators, built for speed and agility. Their famous sickle claws were probably used to grip prey while the jaws delivered killing bites, a technique that works better when multiple individuals can attack simultaneously. In our alternative timeline, the dromaeosaurid lineages might have diversified to fill roles similar to modern wild dogs and wolves, pack hunters that run down prey through persistence rather than ambush. Imagine a pack of Miocene dromaeosaurids, 2 meters long, covered in streaked feathers that break up their outlines against the grass. They hunt in groups of 20 or more, communicating through calls and body language, coordinating their movements across kilometers of open terrain. Their strategy is simple but effective. Identify a target, pursue it until it tires, take turns keeping pressure on while others rest. It is the same strategy used by African wild dogs today, and it is devastatingly effective against prey that relies on speed for survival. No animal can run at maximum speed forever. Eventually, exhaustion wins. The troodontids represent perhaps the most intriguing possibility. These were the intellectuals of the dinosaur world. Small, lightly built theropods with the largest brain-to-body size ratio of any known dinosaur. We will explore their potential in more detail in the next chapter. But they would have been formidable grassland predators in their own right, probably hunting smaller prey that the larger predators ignored, perhaps developing more sophisticated social structures than any of their relatives. The Miocene grasslands in our alternative timeline would have been a killing ground, patrolled by predators at every scale. At the top, packs of slimmed-down tyrannosaurs, still the largest land predators on Earth. but fundamentally transformed by 50 million years of adaptation to new conditions. In the middle, packs of dromaeosaurids running down prey through sheer endurance. At the bottom, troodontids and other small theropods hunting everything from rodent-sized mammals to insects to each other. The age of the lone giant was ending. The solitary tyrannosaur killing through overwhelming individual power was giving way to something new. Predators that succeeded through cooperation, coordination, perhaps even the beginnings of something we might call strategy. In a world of open plains and vigilant herds, brains were becoming as important as brawn. And that raises a question that paleontologists have debated for decades. Given enough time, another 50 million years, say, could dinosaurs have evolved true intelligence? Could they have developed minds capable of understanding the world, of planning for the future, of asking questions about their own existence? The answer is more complicated than you might think. In 1982, a Canadian paleontologist named Dale Russell published a thought experiment that would become one of the most famous and most controversial pieces of speculative paleontology ever written. Russell had been studying Troodon, a small theropod dinosaur from the late Cretaceous known for having an unusually large brain relative to its body size. Looking at the trend of increasing brain size in this lineage, Russell asked a simple question. What if the dinosaurs had not gone extinct? What might Troodon's descendants have become after another 66 million years of evolution? His answer was the dinosauroid, a hypothetical creature that stood upright on two legs, had manipulative hands with opposable digits, and possessed a large rounded brain case capable of housing human-level intelligence. Russell even commissioned a sculpture of his dinosauroid, and the result was strikingly humanoid. Two forward-facing eyes, a vertical posture, a body plan that looked more like a gray alien than a dinosaur. The implication was clear. Given enough time, dinosaurs might have evolved intelligence comparable to our own. We might have had competition. The dinosauroid hypothesis captured the public imagination, but it was criticized almost immediately by other scientists, and the criticism has only intensified in the decades since. The problem is not the idea that dinosaurs might have become more intelligent. That is reasonable speculation supported by the evidence we have. The problem is the assumption that intelligence inevitably leads to a humanoid body plan. Russell's reasoning went something like this. Intelligence requires a large brain. A large brain requires an upright posture to balance it on the spine. An upright posture requires the forelimbs to be free from locomotion. Free forelimbs naturally evolve into manipulative hands. Therefore, any intelligent creature will eventually look more or less like a human. It is a seductive argument, but it is almost certainly wrong. Consider the most intelligent non-human animals alive today. Crows and parrots have demonstrated cognitive abilities that rival great apes. They use tools, solve complex problems, recognize themselves in mirrors, and appear to understand concepts like cause and effect. Yet they look nothing like humans. They are birds, with wings and beaks and bodies shaped coordination, if grassland life required better spatial memory, if complex social structures required recognizing individuals and remembering relationships, then the troodontid brain might have continued to expand. How far? That is impossible to say with certainty, but we can look at what happened with birds, the only dinosaur lineage that survived the extinction, for clues. Crows and parrots have brain-to-body ratios comparable to great apes, and they evolved that level of encephalization in roughly the same 66 million years that we are imagining for our alternative troodontids. It is not unreasonable to suppose that a lineage starting with troodon's already impressive brain might have reached similar levels. Picture a troodontid of the late Miocene, perhaps 10 million years ago in our alternative timeline. It is about 2 meters long from snout to tail tip, covered in feathers that range from gray on the back to white on the belly, camouflage for the open grasslands where it hunts. Its eyes are large and forward-facing, providing excellent binocular vision. Its hands retain 3 clawed fingers, capable of grasping and manipulating objects with a precision its Cretaceous ancestors could not have managed. And its brain, housed in a skull that bulges noticeably at the back, is the largest of any land animal on Earth in proportion to its body size. This creature is smart, not human smart. We will get to why in a moment, but smart in ways that matter for survival. It hunts in packs of 10 to 20 individuals, and the coordination of those hunts is remarkable. Flanking maneuvers, diversionary tactics, even what appears to be deliberate deception, with some individuals feigning injury to lure prey into ambushes. It uses simple tools, sticks to probe burrows for hidden prey, rocks to crack open hard-shelled food items, factors, each one necessary but not sufficient on its own. Primates reached Africa, but the 3 times they reached North America, none of those lineages evolved large brains. Grasslands appeared on every continent, but only in Africa did they produce a species capable of abstract thought. Intelligence of some kind might be common in the universe, but intelligence like ours, capable of technology and science and philosophy, might be vanishingly rare. Our alternative troodontids would have been intelligent, perhaps as intelligent as crows or dolphins or chimpanzees. They might have used tools, formed complex societies, passed knowledge from generation to generation. But the spark that lifted our ancestors from clever ape to wondering human, that spark might never have occurred in a dinosaur lineage, no matter how many millions of years it had to evolve. The dinosaurs could have produced creatures that thought, but not creatures that wondered why they thought. And yet there is something almost comforting in that limitation, because it means that in our alternative timeline the Earth would have remained wild, beautiful and brutal and utterly indifferent to meaning. A planet of animals doing what animals do, without anyone there to call it magnificent or terrible or ask whether it had any point at all. The dinosaurs would have ruled for 230 million years, unchallenged, unmarked by any species capable of recording their existence. In that world, there would be no one to miss us, because there would be no one to know we might have been. 2.5 million years ago, the Earth crossed a threshold, the long cooling that had begun in the Oligocene, that had transformed tropical forests into temperate woodlands and woodlands into grasslands, finally reached its logical conclusion. Ice sheets began to form in the northern hemisphere, not just on isolated mountain peaks, but spreading across entire continents, burying Scandinavia and Canada under kilometers of frozen water. The Pleistocene had begun. And with it came a climate regime unlike anything the planet had experienced in over 250 million years. The ice did not advance once and stay. Instead, it pulsed, advancing during glacial periods that lasted roughly 100,000 years, retreating during interglacials that lasted 10,000 to 20,000 years. Over the course of the Pleistocene, there were more than 20 of these cycles, each one reshaping the planet's geography, pushing ecosystems toward the equator and then allowing them to rebound, creating and destroying land bridges, forcing species to adapt or die. In our timeline, this era produced the iconic megafauna of the Ice Age, woolly mammoths with their shaggy coats and curved tusks, woolly rhinoceroses built like furry tanks, cave bears that stood 3 meters tall on their hind legs, giant ground sloths the size of elephants. These animals evolved specifically for glacial conditions, massive bodies to retain heat, thick fur or fat layers for insulation, the ability to survive on sparse vegetation during the long winters. They were the defining creatures of their age. In our alternative timeline, there would have been no mammoths, no woolly rhinos, no giant sloths. Those niches, large, cold, adapted herbivores, would have been filled by something else entirely. They would have been filled by dinosaurs. The question is whether dinosaurs could have survived the ice ages at all. This is their greatest test, the challenge that would push them further from their evolutionary comfort zone than anything they had faced before. For 200 million years, dinosaurs had thrived in a greenhouse world, warm, wet, forested. The grasslands of the Miocene had been a significant change, but temperatures had still been mild by Pleistocene standards. Now they would face winters where temperatures dropped to -40 degrees Celsius, where snow covered the ground for 8 months of the year, where food became desperately scarce and survival required either migration or the ability to endure months of privation. Could they do it? We have reasons to think they could. Remember the Prince Creek Formation in Alaska, where dinosaurs lived year-round above the Arctic Circle during the Cretaceous. Remember that feathers evolved specifically for insulation. That many dinosaur lineages were already equipped with nature's most effective cold weather clothing. Remember that birds, living dinosaurs, thrive in some of the coldest environments on Earth today, from penguins in Antarctica to snowy owls in the Arctic tundra. The adaptations required for Pleistocene survival would have been significant, but they would not have required dinosaurs to become something fundamentally different. They would have required them to become more of what they already were. Consider the ceratopsians, those horned herbivores that had already adapted to grassland life in the Miocene. A Pleistocene ceratopsian would have been a magnificent creature. Imagine something like a triceratops, but transformed by 60 million years of adaptation to increasingly harsh conditions. Its body would have been massive, perhaps 8 or 9 meters long, bulked up with fat reserves that could sustain it through the lean winter months. Its frill, once used primarily for display and thermoregulation, would have shrunk and thickened, becoming more functional, less ornamental, and covering its entire body from the tip of its nose to the end of its tail would have been a dense coat of feathery integument. Not the elaborate plumage of a tropical bird, but the thick insulating down of an animal built for survival in extreme cold. Picture this creature on a Siberian steppe during an interglacial period, moving in a herd of hundreds across a landscape of grass and low shrubs. It looks almost mammalian at first glance. That shaggy coat, that massive bulk, but the silhouette is unmistakably dinosaurian. The four-legged stance, the beaked face, the horns protruding from the brow. It feeds on tough, low-growing vegetation. Its dental battery grinding plant material with an efficiency that no mammal could match. When winter comes, it will migrate south, following the retreating warmth, returning north only when the snows melt and new growth appears. The hadrosaurs would have faced similar pressures and likely developed similar solutions. Their sophisticated feeding apparatus, those dental batteries with hundreds of interlocking teeth, would have served them well on a diet of tough Arctic vegetation. Their bipedal ancestors had long since given way to animals that walked on all fours most of the time. Their bodies low and wide and heavily insulated. In the winter months, they would have congregated in valleys that offered some protection from the wind, huddling together for warmth. The way musk oxen do today, the predators would have adapted too. A Pleistocene tyrannosaur, descended from the pack-hunting lineages of the Miocene, would have been a creature of nightmares, smaller than its Cretaceous ancestors, perhaps only 5 meters long, but covered in a thick coat of white and gray feathers that rendered it nearly invisible against a snowy backdrop. It would have hunted in coordinated packs, taking down prey many times its individual size through teamwork and persistence. In the depths of winter, when prey was scarce, it might have been able to slow its metabolism and enter a torpor-like state, surviving on stored fat until spring brought new opportunities. But not all dinosaurs would have adapted to the cold. Some lineages would have retreated to the tropics, surviving in equatorial refugia where sequence of events in African primate evolution would have played out differently, or not at all. The Pleistocene would have ended without anyone there to name it, but the glacial cycles themselves would have continued, advancing and retreating on their 100,000-year rhythm. And with each cycle, the dinosaurs of the frozen world would have migrated and adapted and survived, as they had survived everything else the planet had thrown at them. After 230 million years, they had become the ultimate survivors. The ice was just one more challenge, and they had met it. There is a rule in biology called Bergmann's rule, and it is remarkably simple. Within a species or lineage, individuals tend to be larger in colder climates. The reason is thermodynamics. A larger body has a smaller surface area to volume ratio, which means it loses heat more slowly. In a cold environment, being big is an advantage. You can retain your body heat more efficiently. You can store more fat to survive lean times. You can simply endure conditions that would kill a smaller animal. Bergmann's rule shaped the megafauna of our Pleistocene. Woolly mammoths were larger than their tropical elephant relatives. Cave bears dwarfed modern brown bears. The giant deer of Ireland carried antlers spanning 3.5 meters, absurdly large, almost comically oversized, but supported by a body massive enough to carry them. Cold-made giants. In our alternative timeline, the same rule would have applied, and it would have produced giants of a very different kind. The ceratopsians of the Pleistocene steppes would have been the largest members of their lineage since the days of the Cretaceous, perhaps larger. A full-grown adult might have measured 10 meters from beak to tail, standing 2.5 meters at the shoulder, weighing 8 or 9 tons. Its horns would have been shorter than those of Triceratops, less elaborate, more functional weapons for defense against predators and competition for mates rather than the ornate display structures of its ancestors. Its body would have been barrel-shaped, packed with the fat reserves and fermentation chambers needed to process enormous quantities of low-quality vegetation during the brief Arctic summer and survive the long winter on stored energy. These animals would have moved in herds that darkened the horizon, not dozens or hundreds, but thousands, rivers of flesh flowing across the mammoth steppe, following the seasonal pulse of vegetation growth. In summer, they would have pushed north into the high Arctic, grazing on the explosion of plant life that the endless daylight produced. In winter, they would have retreated south, congregating in valleys where snow was less deep and some vegetation remained accessible. The scale of these migrations would have been staggering. Millions of animals moving in synchrony across thousands of kilometers, one of the great wildlife spectacles of the planet. The hadrosaurs would have shared these grasslands, their populations perhaps even larger than the ceratopsians. Their dental batteries gave them an edge in processing the toughest vegetation, and their ability to walk on either 2 or 4 legs might have proved useful in deep snow, where they could rear up to browse on shrubs and low trees when ground-level vegetation was buried. Picture a Pleistocene hadrosaur, 7 meters long, its body covered in a dense coat of filamentous feathers that trapped warm air against the skin. Its duck-like bill adapted for cropping vegetation close to the frozen ground. It moves through a snowstorm in a herd of several hundred. The animals pressed close together for warmth, their breath forming clouds in the frigid air, but the northern steppes were only part of the story. The Pleistocene world was a patchwork of different environments, and each would have produced its own characteristic dinosaur fauna. Beringia, the land bridge that connected Asia and North America during glacial periods, would have been a highway for dinosaur migration, just as it was for mammoths and humans in our timeline. Species that evolved in Asia would have crossed to the Americas and vice versa, creating a shared fauna across the northern continents. The tyrannosaurs of Siberia would have been cousins to the tyrannosaurs of Alaska. separated by only a few thousand kilometers of continuous habitat. The ceratopsians of Mongolia would have mingled with the ceratopsians of Wyoming. It would have been a single great ecosystem stretching from France to Florida, united by the cold. Further south, the tropical refugia would have preserved something very different. In the Amazon basin, in the Congo, in Southeast Asia, fragments of the old forest world would have persisted through the glacial cycles, warmed by their equatorial location even as ice sheets buried the higher latitudes. Here you might have found dinosaurs that looked almost Cretaceous, sauropods still browsing in the canopy, small theropods hunting in the understory, a world that time had almost forgotten. These refugia would have been islands of biodiversity, preserving lineages that had gone extinct elsewhere, serving as sources for recolonization when the ice retreated. The predators of the frozen world would have been as impressive as their prey. The pack-hunting tyrannosaurs we imagined in earlier chapters would have reached their peak in the Pleistocene, their social structures refined by millions of years of evolution, their hunting strategies honed to perfection. A pack of Pleistocene tyrannosaurs taking down a full-grown ceratopsian would have been a spectacle of coordinated violence. Some individuals driving the prey, others cutting off escape routes, still others waiting in ambush. The whole group working together with a precision that spoke to generations of learned behavior passed from parents to offspring. Smaller predators would have filled other niches. The dromaeosaurids, those feathered pursuit hunters, would have been common on the open steppes, hunting in packs that could number in the dozens, taking down mid-sized prey through sheer persistence. Solitary hunters might have stalked the forest edges, ambushing prey from cover, and the troodontids, those large-brained, tool-using hunters we imagined in Chapter 9, might have become the most versatile predators of all, capable of. Imagine yourself standing on a hilltop in this alternative world, looking out across vast plains stretching to the horizon, herds of massive ceratopsians moving like living rivers.